Raoult's Law by Annie Curie, Brianna Mancuso, Evan Dennison, and Mike Schaefer.
History and development. In the 1880s, French chemist François-Marie Raoult discovered that when a substance is dissolved in a solution, the vapor pressure of the solution will generally decrease. Raoult dissolved various non-volatile compounds in different solvents, and he found that the fractional reduction in vapor pressure was equal to the mole fraction of the dissolved solute. This provided a universal relationship between liquids and solutions. Raoult conducted similar work regarding melting point reduction of a liquid based on dissolved substances.
Raoult's law states that the vapor pressure of a solvent above a solution is equal to the vapor pressure of the pure solvent at the same temperature, scaled by the mole fraction of the solvent present. Adding a solute lowers the vapor pressure, as the additional solute particles will fill the gaps between the solvent particles and take up space. This means less of the solvent will be on the surface and less will be able to break free to enter the gas phase, resulting in a lower vapor pressure. If the vapor pressure is less than predicted, a negative deviation, fewer molecules of each component than expected have left the solution in the presence of the other component, indicating that the forces between unlike molecules are stronger.
Solutions are different than pure substances. The saturated vapor pressure of a solution is less than the vapor pressure of the pure solvent at any temperature. This is due to changes in the phase diagram. Boiling point is elevated in a solution and the freezing point is depressed in a solution. In volatile solutions, the solute will exert its own vapor pressure. This means that it needs to be included in the calculations. In non-volatile solutions, the solute will not exert its own vapor pressure. It is not considered in the calculations.
So this is the equation for Raoult's law, which is YIP is equal to XI saturated at a certain temperature, where Y1 is the mole fraction of the gas in the vapor component, P is the total pressure, X1 is the mole fraction of the liquid component, and P1 saturation is the vapor pressure, where vapor pressure is defined as the pressure exerted by a vapor in thermodynamic equilibrium with its condensed phases at a given temperature in a closed system. It is an indication of a liquid's evaporation rate.
For a system with a single condensable species, Raoult's law can be simplified to the equation Y sub I P equals P star sub I of T. This modification is very useful because it is applicable to several problems with similar systems. Note that in this equation and the general form, vapor pressure is written as a function of temperature and not multiplied by it. If P star sub I equals P sub I, the vapor is saturated, meaning that it is unable to hold any more water. If P sub I were to increase, some vapor must condense. The temperature at which this happens is known as the dew point.
Ideal versus non-ideal. When using Raoult's law, it is assumed that the vapor behaves like an ideal gas. It is also assumed that the liquid is an ideal solution. In an ideal gas, molecules have negligible volume, molecules exert no force on each other, and collisions are elastic. In an ideal solution, conditions are the same as an ideal gas, except the intermolecular interactions are equal to those of pure components.
Limitations. Raoult's law only covers cases where two liquids are entirely miscible. This means that it does not cover cases where one liquid floats on top of the other, which would be immiscible liquids. In reality, there is no such thing as an ideal solution, but this can be applied to solutions that most closely resemble the ideal gas requirements. Ideal mixtures are composed of materials that are similar in their molecular size and van der Waals attractions. It is also necessary that there is no enthalpy change in mixing, meaning that there is no change in temperature when the solutions are mixed.
With a single condensed noble species, Raoult's law is an approximation that is generally valid when X1 is close to 1. Henry's law is used when X1 is close to 0, which is used for dilute solutions. A gas in equilibrium with a liquid must be saturated with the volatile components of that liquid. The partial pressure of a vapor at equilibrium in a gas mixture cannot exceed the vapor pressure of the pure component at the system temperature. So now we're going to talk about the difference between saturated and superheated vapors. So in the first case, the vapor is saturated, and in this, any attempt to increase the partial pressure will lead to condensation. And in the second case, a vapor present in a gas less than its saturation amount is referred to as superheated vapor, which means you can still add to the vapor. So the dew point is the temperature where if a gas containing a single superheated vapor is cooled at a constant pressure, the temperature at which vapor becomes saturated is referred to its dew point.
Application of Raoult's law. It relates partial pressure of species A and the mole fraction of A in the liquid phase. Typically, Raoult's law is used in conjunction with Antoine's equation, the equation shown on this slide. You will see this applied in the following example. It can also be used to determine molar concentrations in either vapor or liquid phase.
For our example problem, we're going to have an equimolar liquid mixture of benzene and toluene, which is in equilibrium with its vapor at 30 degrees Celsius. What is the system pressure and composition of the vapor? So before you start this problem, make sure you get all the relevant information. So make sure you look in the back of the book to get the Antoine's equation constants. So plug those constants into the equation for Antoine's equation and make sure you put in 30 degrees Celsius for the temperature and not the temperature in Kelvin. And to get the proper pressure, make sure you get rid of the logarithm, which is on the left side of the equation. Once you get your value for benzene, make sure you do the same thing for toluene and use the same thing. So use the constants that you find in the back of the book and use the correct temperature. After you do that, what you need to do is you need to apply Raoult's law and multiply the vapor pressure by the molecular composition. So each species is half, so you would multiply both of these by a half to get their partial pressures. So you get 59.5 for benzene, and then you get 18.36 for toluene. Then to get the total pressure, you want to add those two together. And by adding those two together, what you can do is you can figure out the composition in the gas phase of these two.